Wonderful. Well, thanks to the organizers for inviting me to speak today. I'll also talk about sensitivity analysis, also using L-square values. This is a project together with my supervisor, Jingyan Zhao, who's also on the panel and will answer some questions during my talk. So I thought it would be a good idea to start with a little review of the sensitivity analysis in literature. I think one of the biggest examples comes from 1959 from Cornfield, arguably one of the biggest successes for causal inference as a field, where he argued that smoking is actually causally related to lung cancer, because if it wasn't, there must be an unmeasured confounder that is at least 9 times as strong in smokers than it is in non-smokers. Later on in the 80s, Rosenbaum proposed his famous sensitivity model, where he looked at a matched study where patient I is matched with patient N plus I. And the sensitivity model includes a bound on the odds ratio of the treatment assignment probabilities. Now, in recent decades, there has been a lot of new work on sensitivity analysis. Just picked a couple of things here, for example, the E-values or the marginal sensitivity model, which I think even goes back to a paper by Tan in 26. There are some methods for instrumental variables and many more, like time series, non-parametrics. So it's actually quite a big literature being built up in the last couple of years. But when we look into practice, we see that many of these models are just not used. And when we thought about this, it appeared to us that one of the main reasons is that most of the work actually focuses on deriving closed form solutions under their sensitivity models. And if you aim to get a closed form solution, you often restrict yourself to consider a very simple sensitivity model, or you may use sensitivity parameters that make sense in a model but are not easy to communicate to applied researchers. So what we propose is to use a new perspective or kind of a new setup of the problem. So we assume that we have that there's a data sample, variables v and variables u, but we have only access to v. So our variables u are unmeasured. The thing we care about is the objective beta. In the context of causal inference, this would usually be a causal effect, and we assume that this beta is a function of two kinds of parameters, theta and psi. So theta are parameters that are estimable, meaning that they only depend on the marginal distribution of v. Because we have access to a data sample of v, we are able to construct an estimator for theta. On the other hand, we have psi, which we call sensitivity parameters, and they in general may depend on the whole distribution. And because this includes u, we can't really estimate them because we don't have data for u. So how can we still get an estimate or do inference for the objective? Well, we may consult domain experts. So if I have identified this sensitivity parameter, I might ask an expert to tell me something about the constraints that they think that the sensitivity parameter needs to fulfill. And these constraints can come in two ways. They can be inequality constraints or equality constraints. And now that we have these constraints on our sensitivity parameter and got some knowledge about it, we can frame sensitivity analysis as an optimization problem. So we take our objective, plug in the theta value, which in the population we have, and then we minimize or maximize over the sensitivity parameter subject to the constraints that are specified. Now, to be clear, beta, g, and h are functions that are fixed. Psi is the optimization parameter, and theta in the population is known, because in the population we have the whole distribution. If we only have a data sample, we may plug in an estimate for theta. The rest of this talk will apply this framework to a specific example, and we go through all of the steps. We first determine which objective we're talking about, then we figure out how we parameterize theta and psi, and last but not least, we look at how we set up these constraints such that it's easy for applied researchers to specify them. The model that we're looking at is quite easy. We assume that all of the relationships are linear from here on, and we have a one-dimensional treatment D, one-dimensional treatment outcome Y. We're interested in the causal effect of D on Y. We also have a couple of baseline covariates and a one-dimensional potential instrument. We could also absorb this instrument into the covariates. And the big issue here is that there's this unmeasured variable u around. For the sake of this talk, it will be one-dimensional. Now, the objective that we're interested in is the causal effect of D and Y. And if we observed data for all of these variables, we could just regress Y on U, D, X, and Z, and then just take the regression coefficient corresponding to D. And this we denote by this expression here. But since we don't know U, we must use another strategy, and the two most common ones are ordinary least squares, and the other one, the two-stage least squares. So ordinary least squares just does the same. We regress Y on the variables, but here we don't include U because we don't have data for it. And if these causal links between U and Y and U and D, if at least one of them does not exist, then this ordinary least squares actually is the same as our objective. So we get a consistent estimator this way. If both of them do exist, then we might try to use an instrumental variable approach and use the two-stage least squares estimator. And if Z does not have a direct effect on Y and Z and U are not correlated, this also is a consistent estimator. But in general, we might have all of these errors here, and we need to do sensitivity analysis. Okay, so having defined our objective, now let's look at the parameters. And our idea here is to use R values or R square values, which was, I think, prominently proposed for the first time in this paper by Snell and Hazlett. So a little bit of notation here for this slide and the next one. Y is a random variable, X, W, and Z are random vectors, and we denote the residual of Y after regressing out X by this term here. Here I have a couple of definitions for you. So let's start with the R square value. So this is a measure that takes values in between 0 and 1. If r square is close to 1, then x does a very good job of explaining variation in y. So this term here in the numerator would be close to 0, and the whole r square would be close to 1, the other way around. If x doesn't explain a lot in y, then this measure is close to 0. And the reason why we choose these r square values is as a tool for parametrization is that they're fairly interpretable, and applied researchers probably already use them in their analysis. So I think it's more intuitive for them to also use them for sensitivity analysis. We can also define a partial version of the r square value. So this is basically just saying we first regress out all of the effects of z and then look at how good x is explaining y. Now, if y and x as variables are actually one-dimensional, then the r square value is just a squared correlation. So if y and x are one-dimensional, we can also define an r value just as the correlation, and by extension also a partial r value. And the last bit of notation that I need is the f value. So this is just a monotone transformation of the corresponding r value. Basically use it to make notation a bit easier. You might have already been wondering what this r square value is, r square calculus is about from the title, and it's actually a couple of algebraic relationships that relate r square and r values. None of them is actually new, like they go back quite a long time, but I haven't seen them written down as like a calculus of their own, and this is what we do in the paper. I think we don't need to go through all of them, but may want to highlight, for example, this one here, saying that if some covariates x and w are independent, then the joint r square value is equal to the sum of the individual r square values. This is kind of it's a very intuitive rule. Or for example, we have the recursive definition of partial correlation, which is also fairly wide known in the literature. These rules here will help us both as a toolbox to express things in terms of r values, and later on they will also help us to define these equality constraints h in the optimization procedure. So we already know what the objective is, and we know how we want to parameterize it. Now we actually need to do it. And to this end, it's helpful to consider the class, or the K-class family of estimates. This is also quite an old concept which cropped up in economics in the 60s. And this is basically a family of estimates and associated estimators with hyperparameter K, which interpolate the common ones like the two-stage least squares and the OLS estimators. In a paper, we derive a new formula for the bias of this estimate, which is the difference between, well, the K-class estimate and the causal effect that we care about. And we see it can be expressed in terms of a couple of r values, r square values, f values, and this fraction of standard deviations. And this formula actually helps us to identify our objective B. So if we just bring over our B-class estimate on the other side, we see that the objective that we care about, our beta, is identified in terms of these black parameters here, which we can estimate because they only depend on observable data. So these constitute theta, and we have this blue and this red term here, which also depend on u, and we use those as our sensitivity parameters psi. So next on, we look at the constraints that we want to put on our sensitivity parameter. So the easiest way of doing it is just directly bounding them. So for example, if a researcher is happy to specify a range that this red or this blue sensitivity parameter can take, then we can directly take this and solve the optimization problem. But sometimes these R-square values or R values are not all that interpretable. So we want to offer researchers a second option. And to this end, we need an additional assumption. And that is that we can split up our covariates into two groups, x dot and x tilde. And we assume that x dot is conditionally independent of u, conditioning on x tilde and z. And if we do that, we can also offer the option of a comparative bound. For example, this one here. And what we do with comparative bounds is we compare how good the unmeasured confounder u can explain variance in y compared to an observable covariate x dot j. So more formally, the statement up here means the unmeasured confounder u can explain at most twice as much variance in y than x dot j does, conditional on all of these other variables here. The strength of this bound here is that we can directly compare the unmeasured confounder with something observed. Okay, so now let's take this constraint here and this constraint here and solve our optimization problem. So for our model here, the optimization problem looks like this, and we optimize it subject to these bounds that we found on the first slide. Now, the sensitivity parameter is already bounded by this bound here, but this one here doesn't correspond to the blue sensitivity parameter, so we need to do some more work. And this is really where the R-square calculus comes in, because if we apply rule 5, we get this additional equality constraint here, which relates the sensitivity parameter here to this new one in green over here. Now we're already a bit closer to the blue one because the only difference is that here we condition on D and here we don't. Then we can consult the R-square calculus again and get one more equality constraint, which now also incorporates the red arrows, the red sensitivity parameters. So now we found a way to link this inequality constraint all the way back to our initial sensitivity parameter. So if we include these other two equality constraints, 2 and 3, we can actually make this bound operational. Now this was still a fairly easy example. In the paper, we derive a lot of different bounds. Broadly, they fall into 4 categories. We reason about the influence of u on D, u on Y, which are the classical regression identification assumptions. We also have bounds for correlation between u and Z and the effect of Z on Y. Now these regression-related sensitivity bounds were already proposed by Snell and Hazlett, so they pick one of each and then give us a closed form solution. But if we don't require a closed form solution and just let the computer solve the optimization problem, then we can combine these bounds in any way. So the researchers, applied researchers, really free to choose how to express their opinions about the sensitivity parameters. So now let's apply this in on an actual data set. And here we use the one that was analyzed in this paper by Card. And here we want to assess how education causally affects salary. So we have this data set, including a couple of baseline covariates, like years of labor force experience, indicators for living in the southern USA, being Black, and living in a metropolitan area. We also have a proposed instrument, which is growing up close to a four-year college. Now, there are a lot of potential unmeasured confounders that we can reason about, but for the sake of illustration, we just focus on motivation here. Now, if we want to do sensitivity analysis in the setting here, first thing we do is we partition our baseline covariates into x dot and x tilde. So here we assume that x dot is the indicator for being Black and x tilde is everything else. The assumption that we make now translates to motivation is independent of being Black, conditional on all of these other variables, which I think are reasonable, which I think is a reasonable assumption. And in terms of bounds, we can specify a whole lot. In this example here, I just picked one comparative bound from each of the 4 different categories. And then I added them in different combinations to the optimization problem. And these are some of the results that we get. So I think we can focus on the first 3 to begin with. So these are the point estimates and the corresponding 95% confidence intervals for the OLS estimators and the 2-stage least square. And on the right side here, we have results for the solution to the optimization problem under different sets of constraints. So in the first one here, I solved the optimization problem over this constraint on U on D and U on Y, and got this blue interval here. And if we now solve this optimization problem over a bootstrap sample, we also get a 95% sensitivity interval. With sensitivity interval, we just mean the natural extension of a confidence interval. Now, if we only impose the 2 IV-related bounds, B3 and B4, we see that the analysis, that the picture changes quite a lot. And both this partially identified range in blue, as well as the sensitivity interval, gets super wide. If we add either B1 or B2 to these bounds here, we can actually reduce the size quite a bit. And if we add all 4 of them, we get the same result as for just the first 2 constraints. So we can see that in presence of these regression related bounds, the IV bounds don't seem to contribute anything to the sensitivity analysis. Now for the sake of time, I think I might skip this plot here and tell you some more about other things that I didn't talk about, but which are covered in the paper. So first of all, the R-square calculus can actually be extended to Hilbert spaces. In the paper, we also talk about what to do with multiple unmeasured confounders. Moreover, we actually we also talk about how we actually solve the optimization problem that results from posing R-square related constraints, and we investigate more the coverage probability, the coverage of these of different approaches to construct sensitivity intervals. Moreover, we offer some additional visualization tools for applied researchers. So in conclusion, we introduced a new framework for sensitivity analysis by casting it as a constraint optimization problem, and thus giving researchers a lot more opportunity to express their domain knowledge. We introduced the R-square calculus as a system of its own, which is quite handy. And we conducted sensitivity analysis in a linear model using R values. We proposed flexible and interpretable bounds for researchers. And last but not least, we applied this on a data set. If you're curious, the paper is on arXiv. The updated version should appear tomorrow, I think, but if you can't wait, it already is available on my website. Thank you, and I'm happy to take questions.
Yeah, thanks for the nice talk, Tobias. I have a quick question. So the framework that you described, does it also generally work for any like DAG that I have? So more complex factors. Let's say, for example, I have a mediator, and then like there's some confounding that I'm worried between treatment and mediator, and maybe there's like another confounder between mediator and outcome. Does this R squared calculus like also cover all of those cases?
In principle, yes. So the R-square calculus relies on the assumption that things are linear, but all of the rules here, they are kind of agnostic to where I apply them. So if, for example, I have another DAG, I could also reason about sensitivity parameters in there with applying rules of the R-square calculus. I think there are already some papers that kind of implicitly use some of the rules of the R-square calculus. But in general, I think it's hard to automate this. So I think it would be really nice if there was software where we can just input a graph, select what are unmeasured confounders, and we get some identification results in terms of these R-square values. I think this in general is quite hard, but if you want to sit down, do the algebra, then this R-square calculus extends to other settings too.
Okay, great, thanks. And another thing that you mentioned is like an extension to like multiple confounders. So what happens intuitively? Are the bounds still sharp in that setup, or like what happens, or does the optimization problem get more difficult, or is it all kind of like as simple as the one-dimensional U case?
Mm-hmm. So if my U here is multidimensional, then I could get some canceling effects. For example, one unmeasured variable might slightly bias the causal effect upwards, the other one downwards, the next two maybe upwards. So if we lump in all of our unmeasured confounder and consider it as one big super confounder in a way, and run through the same procedure with just treating it as one, then we actually get conservative because of these canceling effects. If I want to specify a more fine relationship, like how one unmeasured variable affects U and one unmeasured variable affects D and Y, and maybe is even related to another unmeasured variable, and this becomes quite complicated quickly because just of the involved algebra. In the paper, I give one identification result with 2 unmeasured confounders where we are still kind of sharp, but the number of sensitivity parameters then increases quite a lot.
Okay, thanks. I think there's one more question, but we're running out of time, so I'll just quickly like wrap up and then we can maybe discuss the last question. Okay, yeah, first, thank you so much, Melody and Tobias, for excellent talks. I learned a lot today. It was very interesting. And yeah, thank you all for coming. Next week, we're going to have Jessica Young from Harvard University, who will talk about causal inference with competing events. Thank you all for coming today. I hope you have a great week and see you next time.